Yes, so hello everyone. So I am Anjali Negi. A little introduction. So I am pursuing my PhD in IIT Kanpur in physical chemistry as a theoretical and computational chemist. So today we will see three questions on GATE Chemistry 2017 and yeah, I will share my window and okay, I'll start playing. Hello everyone. In this video, I will be solving GATE 2017 Chemistry question number 38. This question state that if delta naught is the octahedral splitting energy and P is the Hello everyone. In this video, I will be solving GATE 2017 Chemistry question number 38. This question state that if delta naught is the octahedral splitting energy and P is the electron pairing energy, then the crystal field stabilization energy CFSE of this complex coordinate complex is. So we have to find out. Hello everyone. In this video, I will be solving GATE 2017 Chemistry question number 38. This question states that if delta naught is the octahedral splitting energy and P is the electron pairing energy, then the crystal field stabilization energy CFSE of this complex is. So we have to find out the CFSE of the given complex. To the crystal field splitting in an octahedral complex. So in an octahedral complex, this state represents the degeneracy of all the 5d orbital in the isolated central line, and the state 2 represent the hypothetical degeneracy of all the orbital at a higher energy level. If the negative charge of all the ligands is assumed to be uniformly affecting the electrons in the d orbital of the metal line. So the state number 3 is actually this represent the crystal field splitting. So in octahedral complex, as our So in an octahedral complex, the coordination number is 6 and the metal ion is at the center and the ligand occupy the sixth corner of the octahedron. Okay, so we know that the orbitals which are dx square minus y square and dz square are oriented along the axis and the other orbital remain in between the axes which are dxy, dyz and dzx. So in case of octahedral complex, these two orbitals are designated as EG. So in octahedral complex, these two orbitals are designated as EG, and the other three are T2G. Okay. And as the ligand approaches the central line, along the axis, the electron is present in the EG orbital. So is repelled more by the ligand electrons than the in comparison with the T2G1. Hence, we see that the energy of the dz square and dx square minus y square, these orbital, is much more in comparison to the dxy, dyz, and dzx orbitals. Okay. And the splitting energy, that is delta naught, is the crystal field splitting energy, and this is actually, if we say this is from the barycenter, it is plus x, and from the barycenter T2G is stabilized as y. So we will say x plus y, if it is equal to delta naught, which is my CFSC, is equal to 10 dq naught. So my x is in octahedral field is equal to 3 by 5 of delta naught. That is the, in terms of dq, it is 6. And y is 2 by 5 of delta naught. In terms of dq, it is equal to 4. So T2G electrons, each of them is actually stabilized by minus 4 dq. And electron in the EG and EG electron are destabilized by plus 6 dq naught. These are actually with respect to the unsplit barycenter, which is here. And hence we can say that the total energy of the system is conserved before and after splitting. Okay. So the ligands which causes a large splitting delta of the d orbital are referred to as the strong field ligands. And the complex such as uh, uh, this, for example, given below, is called a low spin. And the example of one ligand is NO2 negative. So in this complex that the example is shown below is actually, we can see that the delta naught is so large that pairing is possible in this case. Okay, so we see that no electron is in EG orbital, but there is a pairing. Good. So if we have taken D5, for example, so initially it was all unpaired electron. Okay, and after the strong field ligand, it experience octahedral splitting, uh, where the delta naught value is very large, the CFSE is very large. So pairing take place, and this complex looks something like this. Now, the ligands, for example, iodine I negative and Br negative, which causes a small splitting delta of the d orbital, are referred to as a weak field ligand, and the complexes are known as high spin complex, which are formed. So this is the example of a high spin complex for a D5 electron system, electronic configuration. So we get delta naught as delta naught is very small, so no pairing take place in this. So in high spin complex, always remember that pairing doesn't take place. Okay, so in general, this is a crystal field splitting energy increase as the ligand varies in the following order. So in the following order, if we go from left to right, we see that there are there is an increased value of the delta. So there is a higher splitting, and so I can say that CN negative is a strong field ligand causing a higher delta naught value. Okay. Now let's solve our question. So our question is that yes. So my question was to solve the to find out the CFSE of the given complex. So for the given complex, my cobalt is in 2 plus oxidation state, where I can write the electronic configuration as this, which is 3d7. So 3d7, before I fill up the electrons in the T2g and Eg orbital of the of my complex, I should first note 2 points. The first one is that ammonia is actually is considered as a strong field, but in case of cobalt 2 plus, we see it, that it makes a high spin high spin complex, and in case of cobalt 3 plus, it makes a low spin complex. So yeah, also here you can note that as the charge or the oxidation state of my metal ion increases, it also affects the CFSE, such that as the oxidation state increases, my delta naught values also increases. Okay. What is in high spin, because my so when we fill this, my complex is in high spin, because my oxidation state of my cobalt is 2 plus. So this will be 1, 2, 3, okay, 4, 5, 6, 7, and this was the oxidation state of my metal is 2 plus. So this will be 1, 1, 2, 3. So we note that in high spin, complex, no pairing energy is there. Okay, because no pairing is taking place besides the one which are already paired. So the CFSE of cobalt 2 complex which is given will be So there are total 5 into -3. Naught plus there are 2 electrons, so 2 into 0.6 delta naught, giving me the value of option number C. So the correct option for the question number 38 is that option number C. Okay. For this, I will refer you to go through the lecture Bonding in Complexes 3 by Professor Debashish Ray, Department of Chemistry, IIT Kharagpur. This is the YouTube link for that. Thank you.
So if you have any
Hello
doubt,
everyone. So today I will be discussing three.
you have any doubts? If it's clear, you can just type clear. Okay. So I will move to the second one.
Hello everyone. In this video, I will be solving GATE 2017 chemistry question number 10. This question states that the complex vanadium oxide, chromium oxide, and manganese oxide ion exhibit intense ligand to metal charge transfer transition. The wavelength of this transition follows the order. So we are given that these exhibit ligand to metal charge transfer, and we have to find out the order of the wavelength of the transition. So before that, let's move into some basic. So the charge transfer transition denoted as CT. So the question is that why is it that some transition metal complex are intensely colored in solution but possesses no d electron? So we know that there is a possibility of DD transition and it shows color in the complex. So if there is no electron in the d orbital of the metal, then what is the reason for the color, intense color for a metal complex? For example, KMnO4, where manganese has oxidation of +7 and with the electronic configuration of 3d0, so there is no electron in the d orbital. So it declined the fact of DD transition happening here. But instead of that, it still shows a intense color, KMnO4, like purple. So there are things that we have to note here, that the vacant metal d orbital is a very good acceptor here and can accept the electronic charge density from the ligand system or any oxide system, correct? Because because my d orbital is empty here. In transition metal complexes, change in electron distribution between the metal and a ligand give rise to the charge transfer CT bands. Okay, and this CT absorption these lie in the UV regions and are intense and they where the selection rules are actually allowed. So these have a silent value of up to 50,000 or greater. Okay. Yeah, but in the case of where only DD transition is happening, we see that the delta E is very small for the transition to take place. So when the delta E is very small, the epsilon max value is also very less than or equal to less than 20 liter. Uh, uh, this is also less than 20 liter molar inverse centimeter inverse. So this gives me the points where for good detection, I should actually take a very high concentration solution for this, with or even a higher path length of the cell. Also, this DD transition shows a very less intense color because of the selection rule forbidden DD transition. This result in a weak absorption. However, in the case of the CT transition, we detect it is very detectable in a low concentration of the analyte also, uh, following the law of Beers-Lambert law, where absorbance is equal to silent, B is the path length, which is generally 1 centimeter, and C is the concentration. So in the case of CT transition, it is possible to detect even the low concentration because of the epsilon value, which is Emax, is very high, that is up to 35,000. So the charge transfer transition, particularly for the LMCT, if we talk about, it is from the metal line, and it is in between the metal line orbitals and the ligand orbitals. So the metal ion, when it is in highly oxidizing state and my ligand is in reducing state, then this case will be referred to as ligand to metal charge transfer. And the example for that, as we have discussed, KMnO4, where my O2 negative is highly reducible, and the intensity of the color is due to the fact that there is a high probability of these transitions taking place. And the example are mercury I2, which is brick red in color, and CrO4 2 negative, which is yellow in color. And the charge transfer transition, the CT transition, are actually classified into metal to ligand, charge transfer, so MLCT, or ligand to metal charge transfer, or LMCT. There are other two categories also where there is two oxidation state of metal is present. So it will be a metal to metal orbital. And if there is state of ligand is present, then it will be a ligand to ligand. But here we will focus on the LMCT first. So The ligand have actually the sigma antibonding, pi antibonding type of orbital, also non-bonding orbital, molecular orbital. So if the ligand molecular orbital are full, so the charge transfer may occur. So the charge transfer may occur from the ligand molecular orbital to the empty or partially filled metal d orbital. And for some example I have given here. So for LMCT, very common for coordination compound having pi acceptor ligands. So these are the example of pi acceptor ligands. So in terms of molecular orbital, let's look into. So this is a D6 uncoordinated metal. So D6, okay, and here we have a ligand where it's a sigma orbital, for example. So this is a full sigma orbital. So in octahedral complex, my molecular orbital of the given complex will look like this, where the splitting of degenerate d orbital take place as in octahedral field, following with splitting in T2G and EG orbitals respectively, and then the charge transfer LMCT will take place from sigma orbital here to the one which is empty. So it will be something we can. This is sigma antibonding for it. Okay, so this will take place from the full ligand orbital to the empty metal orbital. So this is the LMCT, and so this will be the energy or the wavelength associated with it will be observed as in the absorption band. Here you can look into this figure where this T2G and EG comes from the metal. Okay, and my EG acts as a sigma antibonding here. Also, the transition that I have shown here is from the sigma. It can actually take place from either sigma or pi to the antibonding of sigma antibonding or pi antibonding. So, for example, here, transition can take place even from the full pi orbital or full pi antibonding to the EG sigma antibonding, correct? So coming to our question, which was asked that these given complexes, we should find out the order of the wavelength of the transition for the LMCT. So for LMCT, so we have to find the wavelength of the given transition. So before that, we have to note that as the Z effective increases, so Z effective is the charge between on my metal orbital, so it is a nuclear charge. So as it increases, it will attract more the ligand orbital, correct? And the so my energy order will be, so ligand will act as a donor and my metal will act as a acceptor. So so the oxidation state is as follows: so vanadium plus 5, chromium plus 6, manganese plus 7. So you can see that the molecular orbital will look like something for the Mn. So this is if it is my Mn plus 7. So my ligand is here. Okay, and for chromium, it will be a little higher. And for vanadium, so overall, the transition from ligand to metal, the energy order will be, so the energy order will be highest in vanadium, and then chromium, and then manganese. So this will be the energy order is, okay. And as we know, my energy is inversely proportional to wavelength, so the order get reversed in the case of wavelength. So my wavelength order will be this. So the correct option for the given question is option number C. Okay, and I will refer you to go through the lecture Charge Transfer by Professor Debashish Ray, Department of Chemistry, IIT Kharagpur. This is the link is attached. Thank you.
So, any doubts?
Hello everyone, good evening. हेलो, एक बार जरा बताना आपको आवाज आ रही है? क्या सभी को आवाज आ रही है? क्लियर स्क्रीन दिखाई दे रही है? यस मैम। वेलकम टू वन स्टॉप नीट, दिस इज श्रुति मैम, और आज हम शुरू कर रहे हैं क्लास 11th का सेकेंड यूनिट मॉर्फोलॉजी ऑफ फ्लावरिंग।
Oh, sorry, that was not me. Actually, one video started playing. Yeah, so if we don't have any doubt, we can move forward.
Hello everyone. In this video, I will be solving the 2017 chemistry question number 6. This question states that the wavelength associated with a particle in a one-dimensional box of length L is, where n refers to the quantum number. So we are given with 4 different options. We have to find the wavelength associated with the particle in a one-dimension box. So the particle in one-dimensional box problem, mathematically we can define it as a particle is bound in a dimension with, for example, x, in x direction, where the length of the box is L and the potential value inside the box is actually 0, but at the boundary it is equal to infinity. So my particle can only be find in between in between x greater than 0 and less than L. And the Schrodinger equation, the time-independent Schrodinger equation for the particle of mass m moving in one direction with the energy capital E, we can write it as minus h square upon 2m. Okay, so this will be d2 psi x by dx square plus Vh psi x equal to E psi x, correct? Here, my h bar is a reduced Planck constant, where the value for this is equal to h upon 2 pi, and my m is the mass of the particle, and psi x is the stationary time independent wavelength, and Vx is my potential energy as a function of the position, and E is my energy. Okay. So the equation, this will get modified for the particle of mass m, which is free to move parallel to the x-axis with zero potential. Okay, resulting in a quantum mechanical description of free motion in one dimension. Okay, so this will be h bar square 2m d2 psi x upon dx square is equal to E psi x, and the energy corresponding to this will be, if we solve all further and find out the energy, the expression comes out to be n square h square upon 8m capital L square. Here, this is the corresponding energy equation for particle in one dimension box of length capital L. Okay. So from here, if I solve my question, so I can also write my energy as P square upon 2m. Okay, it is supposed to be the sum of kinetic energy plus potential, but potential here is 0. So I can just write my energy is equal to the kinetic energy, which is P square by 2m, where my P is the momentum and m is my mass of the particle. So I can write it as this. So this will be, well, n is my principal quantum number. Correct? And my L square will be m square h square 8m so this will give me okay, and yes, so my L will become m h upon 2p, and from de Broglie we know that lambda is equal to h upon p. This is the de Broglie wavelength. Correct? So my L will become n upon 2 lambda. Okay, and what I have to find out, I have to find the lambda value. So it will be 2 upon n multiplied by L. So this is the solution. Yes. So the wavelength associated with the particle in one-dimensional box of length capital L, where n is my quantum number, the correct option is 2 into L upon m. So this is the correct option. I highly recommend you to go through the NPTEL reference Schrodinger equation particle in a one-dimensional box part 1 by Professor Mangala Sundar Krishnan, Department of Chemistry, IIT Madras. There is that link. Yeah, hello everyone. So today,
Yes, so any doubt? Okay. So if you are clear with the videos and the problem we solved, so I will just introduce you. This you might have already studied, but so to start with the one which I have said earlier, that I will give you some tutorial about the HCP CCP. So first of all, we need to know what are the how the voids are formed. So the voids that you have studied must be many types. So the one which you are seeing in your figure, like here, this one is what kind of void it is, if anyone can say.
Tetrahedral void.
For tetrahedral there should be 4 atoms touching each other, but it is only 3 atoms. So the circle represent atoms, so it should be the basic one, I mean triangular void. Okay, so the heading should be the types of void here, and for the first one it will be, for example, if it is atom A, atom B, atom C, so from the center, if we just join all the centers, so this the void that is appearing here is the triangular void. Okay, and the definition is also very simple, that the 3 spheres in the same plane, and the void is formed by the 3 spheres when they touch each other. Okay, so this is the triangular void. And the second one you can see is the 4 atom void. So so it should be, it is again not the tetrahedral, because all the 4 atoms are in the same plane. So what it should be? This is the square plane. ठीक है, तो this void is again formed by touching of the 4 spheres in the same plane, and yes, that is why it's a square planar void. We can actually, by just joining the center and considering the radius of each, we can calculate what is the r upon small r upon capital R ratio, where my small r is the radius of sphere which is my void. Okay, or the sphere which can fit into my void is the small r, and my capital R is the radius of the sphere which are representing my atom. Okay, and the third option here, this one. So this one is again, okay, so I haven't drawn another one. So yes, Ravindra, this one is the one where I will be drawing another atom on the top of the 3, and yeah, okay, so now 4 atoms, but the fourth one is on the top of the 3. So all 4 atoms are touching each other, so this one is the one, making the geometry something like this. So these dots are in the same plane and the other one is on the top of them, so this is forming as a tetrahedral void. Okay, and to actually find out the ratio and the ratio of the void, small r and capital R, for this we have to make mathematically make it as a problem of these two triangles. Okay, and then we will solve it. So I am not actually solving it now. If you guys will want to continue, then I can show it right now or in later class. So for the fourth one, the octahedral void, so I have till now discussed from starting triangular, so this is triangular, then the square planar, then the tetrahedral. Okay, now we are going to the octahedral one. So for the octahedral one, we have a total of 6 spheres touching each other. They will form octahedral void, but there will be it can form in two ways. So I will just write here as octahedral void, 6 spheres, but in two different ways. So one will be, so this is the case number 1 for example, and this will be 3 spheres in same plane. Okay, and the other 3 either upper or at the bottom. Correct. So now the one I have drawn, I can just draw it in reverse. For example, like this triangle pointing there, so that the center of each sphere can be connected to one single dot, and this will be my octahedral void. So in close, if I just put it here, it will be correct. And so all these demonstration I think you are very familiar with, but still we get very weak memory, so we forget it a little. Yeah, so this is the one case number 1 where I can demonstrate my octahedral void in this way. But in second way, what I can do, second way is 4 sphere in a plane plus, so one will be, so 4 is there, so one will be upper in upper plane and the other one will be in lower plane or bottom. Correct. So I have to move. So yes, so it will be something, so 4 plane, 1 2 3 and 4. So just consider all the sphere of same dimension. I mean, not the two are bigger or two are smaller. So yes, this will be just above and the other one will be just below, such that their center will be so just imagine that this one at the top and the one in the bottom, these two are here, I mean placed at the space here. So all together the 6 atoms will touch each other and make a void, which is again the octahedral void but in another manner. So this is what we called a square planar void. But it is actually not exactly the square planar void. This is octahedral void, sorry, but the one in between is similar to the square planar one. So yes, okay. So this is the octahedral void again here. The example for this is SF6. So I have discussed triangular, tetrahedral, octahedral and square planar. So there are 4 voids that I have quickly discussed, and the last one is the one which is very common. I mean, not very common, but it's not a good type of packing, because the packing fraction is very, it's not that much great. So yeah, so cubical void. So the another one is cubical voids. Okay, the last one. So in cubical voids, you can just imagine one cube. Okay, and all the atom or squares or molecule are at the corner of the cube. So now you can see how the atom will touch each other. In one plane there will be 4 atoms, in another plane there will be again 4 atoms, and all them are on top of each other. So this will be something like, okay, so 1 2 3 4, and the next atom or molecule will be on top of this. Okay, so this is the void which is known as a cubical void. Okay, so that's how we know that the packing of the atoms or molecule in a crystal changes, because how the packing is happening changes the void formation, and that's how the packing fraction also changes, correct? So the one that I wanted to discuss with you was close packing in 3 dimensions. So in 3 dimension we have layers of packing. So it will be layer A, layer B, layer C, or either layer A, layer B and layer A again. Okay, so when we are talking about close packing in 3 dimension, so we are talking about the layers. So it can be ABA or it can be ABC. Okay, so I think we should continue it in another class if you are okay, because this is something which I am just I have just wanted to make another effort. So if you guys are, you can give me the feedback. So yes. Ashish Ravindra Gunasli. Yeah, I will close the class. I will discuss this close packing in 3D in another class. You can give me your feedback or have any doubt. Okay. Okay, so thank you. You guys can leave now and we will meet in the next week. Thank you.